Let's compare algorithms. Algorithm comparisons involves measuring efficiencies and typically involves the order of growth analysis. And the order of growth analysis connotes to the efficiency of the algorithms in terms of its time and space. Without getting into too much detail, let's suppose there's a game. It's a guessing game between Alex and Bob. And basically Alex thinks a number, guesses the number, right? And Bob pretty much just guess it. The number that Alex has in mind is anywhere between 1 and 1,000. So Bob says, well, let me think about this strategically. The strategy in guessing this is if I just randomly guess a number and just keep on going, I have to keep track, what I guessed. I'm going to start with 1. And Alice says, no, this is higher. And Bob says it's 2. And no, this is higher. So Bob says 3, right? So the game just keeps going. And what if, in the worst case, Alice thought of a number 1,000 and Bob's, started with 1. So worst case is Bob's going to have to go through this 1,000 guesses in order to get to it, right? Also think of reverse situations where Alex thinks of a number 1 and Bob, strategically, maybe there's a higher chance that Alex would think a higher number. So he would start with 1,000, right? And then 999, 998, so on and so forth. Well, this is a linear search. Linear search is a search algorithm that start from the beginning of an array, right? So what is an array here? Let's just say this array is nums. From the beginning of the array and check each element until the search key is found. So what's search key? Search key is what Alice thinks, right? This key. In short, you can pretty much just express this in terms of a for loop. This is integer I equals 0. So what is I? I less than 1,000. And then you have I plus plus. And then you just write this out. And what is this? If nums I equals, the guess is the key, return I. So this is sequential search algorithm or linear search algorithms. The worst case is 1,000. And of course, when we're getting into the estimations later, this number 1,000 could be expressed in terms of a variable n as in Nancy here. Okay, all right, so let's move on. This sequential search algorithm as an example. What does it have to do with the efficiencies here? The number of iteration that this require to get to it. Let's just suppose that we have a sequence of unambiguous instructions that solves a problem, right, within a finite number of times. Analyzing an algorithm in terms of its speed and space will give us the efficiency. The efficiency is measured in terms of the number of operations that we've got. Unambiguous operation could be addition, subtraction, multiplication, division, or even modulus, or even assignments too, right? So these are unambiguous, meaning it takes constant amount of time to execute these things. If we know the set of instruction that happens inside the algorithms, right, like we just saw from the previous example, we can typically measure its time, like how fast it turns, how much space or how much memory it requires the solutions to execute at runtime. This is how we analyze an algorithm. So if we can formalize an algorithm in terms of this n is going to tell us a lot because this n is a variable. This is a variable. For any computing algorithms, there is a variable. What we're studying is the amount of time it takes, so time and space, right? This is very important. So let's take a look at another example here and see how we can count the number of operations here. In order to measure the complexity of an algorithms, we attempt to count the number of basic operations. Now, this is very important. So what does that mean by basic operations? These basic operations are constant time operations. I just introduced another thing called constant time operations. So constant time operation is basically an operation that for a given CPU or processor, it always operates in the same amount of time, regardless of input values. So what is an example of this constant time? We just talked about, right? Addition, subtractions, multiplication, divisions of any fixed size integer or floating point values. You can also think of assignment of a reference, a pointer, or a fixed size data value to be a constant. So an example is x equals 1,000. An example for this one is 2 divided by 1, right? Or something like that. Or you can have comparison of two fixed size data values, meaning I equals k, right? So this is comparisons of the two fixed size. variable. So this is also constant. Or you can have read or write array elements at a particular index. Num, right? We use this num, right? I equals 4. These are all constant operations. This means if you were to run the same operation that involves these, 100,000 times on a given process, it should take roughly the same amount of time every single time. Now, whenever you see these basic operation or constant time operation, we simply count them. If an algorithm has more basic operations than another algorithm, the former algorithm would be more time consuming to execute. By extension, a longer algorithms at runtime also means that the more memory that this algorithm would take. We need to be cognizant of the number of operations. And typically, when you have a lot of operations, you don't want to count every single one of them. Usually you want to pick the operation that matters the most, typically the more significant ones. Let's take a look at the following examples. This is a pseudocode for the Bob Alice game, but now we formalize it into a function. So this is the function we're looking at here. So this function is called sequential search, high and low sequential search. So just like before, we're talking about 1 through 1,000. So Alice is going to think of a name, a number. Let's just say this is K. The key is a K. Guess is not correct. Means guess is Bob's, not K. So what is set guess to 0? Well, set guess to 0 means guess, and guess is an integer, right? Of course, equals 0. You have this do while loop. So this is actually a loop that loops through, hey, guess is 0, incrementing my guess plus, right? And the bottom one is announce guess. So we know what announce guess. So this is printf, okay? So printf to screen whatnot. So let's just assume that this is it. And Bob has to say, hey, this is my guess. That's basically what announcement is, right? And if you don't count the number of operations we've got here, right? On the number of operations. So this constant time operation we were talking about earlier. So what is set guess here? How many operations do we have? So integer guess equals 0. That's 1, right? There's only one operations, which is that equal sign right there. What is very important is now we got this do while loop. In the worst case, we're going to have to go through 1,000 times. So let's just count the worst case, the number of, right? You don't want to go for the best case. You want to go for the worst case because worst case is the one that you're measuring against. If you take the best case, then, if this thing takes 0 time, because the first one is the guess. Increment guess by 1, right? This guess plus, you got to do 1,000 times, right? Because this is in a get do while loop. Bob says, hey, is this one the one that you're looking for? So Bob's going to have to do 1,000 times, worst case. Guess is not correct. So meaning guess, not K. This is 1,000. So if you add them all up here, we got 3,001. If you formalize this, right, and express this function called sequential search in the form of the number of operations you've got, and this is constant time. Constant time operation means it is an operation, any given processor, it always operates in the same amount of time, regardless of the value. 3,001. Let's just say you come up with another sequential search, and this sequential search has another number associated with it, and that number is 3,002. Then this other sequential search is not as efficient as the first one, which is 3,001. And this gives you, or computer scientists, a general idea of how efficient an algorithm is in terms of the number of operations. That is both in time and space. Sometimes you look at the algorithm and say, hey, this one does not require any storage. Even though the number of operations is 3,001, there's no storage. In this case, there's one storage, which is the guess equals 4. Is 0. So what is integer guess? Integer guess is 4 bytes. So storage is not constant, but the number of time, is 3,001. That's basically it. So we're able to glean insight just by looking at the pseudocode or any computer code, just by counting the number of operations. So we will study the complexities involving best case and worst case scenarios by counting these operations in the next video.